Lesson 4.4, Proportional and Non-Proportional Situations. Lesson 4.4, Proportional and Non-Proportional Situations. Distinguish between proportional and non-proportional situations using a graph. If a relationship is nonlinear, it is non-proportional. If it is linear, it may either be proportional or non-proportional. When the graph of the linear relationship contains the origin, the relationship is proportional. Okay, let's take a look at some examples, starting with example 1.
All right, hey, now here's a question. Suppose that someone gives us a graph of a line. Can we determine if that graph is describing a relationship that is, in fact, a direct variation? Well, that is equivalent to saying, does the graph have an equation of the form y equals kx? If the answer is yes, then we know that, in fact, we do have a direct variation, and if not, we don't. Let's take a look at an example. So here's the graph of a line, which we like, very nice. And is it possible that this graph represents a direct variation? Well, the answer is no. Sorry. But you see, the point is that the equation of this line will not have this form. Why? Because if we write this line in a slope-intercept form, we see that the intercept will be -1. And since the intercept is going to be -1, that means that the equation of this line is going to be y equals kx minus 1, and therefore not of the form y equals kx. So we're seeing something interesting here. If something is going to be a direct variation, it's got to be a line, and it's got to be a special line. The line has to pass through, say it with me, the origin. It's got to pass through the crosshairs of the axes. Otherwise, not a direct variation. So sorry, no dice. But what about this one? It's a straight line, so that's awesome. And notice that it does beautifully go through the origin, 0, 0. And so, in fact, here we see that this is going to be a direct variation. And in fact, if we want, we could actually find that constant. Because remember, the constant just represents the slope. So how would we find the slope? Well, what we do is we find 2 points that we can see. So definitely the origin, 0, 0, is a point on this line. And let's see, where does it cross the other crosshairs of the grid? Right here. And so now, remember, slope is rise over run. So I have to rise up. So this is the slope m. We have to rise up from here 1, 2 units. So we have 2 in the numerator, and then 1, 2, 3 downstairs, 3 in the denominator. And so I see the slope of this line is 2/3. And so therefore that's my k. So you can view that as a k if you want. Think of it as a k. It's a special k if you want. And therefore we have y equals 2/3 x. Now technically we have to add the plus b. But notice that by design, the y-intercept is 0, and that's why, in fact, it is direct variation. So this is a direct variation, and its equation is y equals 2/3 x, and the constant in the direct variation is, in this case, 2/3. Very cool.
All right, let's do a quick lesson tutorial, a quick review. We are identifying a direct variation from a graph. All right, so the main thing you got to realize is if the graph goes through 0, it is direct variation. If it goes through 0, that means it's direct variation, and it means it's proportional. All right, if the graph does not go through 0, that means it's going to be non-proportional. It may be linear, but it's going to be non-proportional. All right, the most important thing to remember here is knowing how to find your slope. You saw what he did. He just went at 0. And then he looked on the grid and you found the crosshair here. All right, you could have also used the crosshair there, but he just used those 2. And we're going to count. Rise, 1, 2. Run, 1, 2, 3. So our slope then is 2/3. But don't forget, slope is also called the constant of variation. And also you learn a new term. The slope is also called the direct variation. So get this part right here in your notes. Direct variation is a linear relationship between 2 variables that can be written in the form y is equal to k times x. Or if you were to solve for k is equal to y over x. And by the way, look, see where k is? Rise over run. Rise over run. That's why it's the same as the slope, which is the same as the constant. The fixed number k in a direct variation equation is the constant of variation. Example 2. Distinguish between proportional and non-proportional situations using an equation. Distinguish between proportional and non-proportional situations using an equation. If an equation is not a linear equation, it represents a non-proportional relationship. A linear equation of the form y equals mx plus b may represent either a proportional, which means that the y-intercept is 0, which is like saying it's going through the axis, or going through the origin, or non-proportional, where b cannot equal 0. So once again, a linear relationship of the form y equals mx plus b may represent either a proportional or non-proportional relationship. Proportional would be if the graph were going through the origin. Non-proportional would be if the graph were not going through the origin, but still linear in both situations.
All right, let's take a look at some functions and see if, in fact, they represent a proportional relationship or not. Remember, a proportional relationship means that we have a graph of a straight line that passes through the origin, and whenever we have a non-zero x and y, the ratio will always be the same. Okay, so let's take a look at an example. Here's one. How about the function y equals negative x? So that means that, what's this function? Whatever you give me for x, y will be the opposite. We'll have the opposite sign. So let's take a look and see if, in fact, this is describing a proportional relationship or not. So what do? I'll just pick some points here. So I'll pick some positive and negative just to kind of stir things up. So I'll consider negative 2, negative 1. I'll do 0. I'll consider 1 and 2. Now, what are the corresponding y values? Well, the function says y is the opposite of x. So if x equals negative 2, the opposite of negative 2 would be 2. The opposite of negative 1 would be 1. The opposite of 0 would be itself 0. The opposite of 1 would be negative 1. And the opposite of 2 would be negative 2. Okay, now we could take a look at ratios of corresponding y to x as long as we don't have zeros, and see if they're equal or not. So here I see 2 over negative 2, which simplifies to negative 1. Now, does that equal the ratio here of 1 to negative 1? Well, 1 to negative 1 actually simplifies to negative 1. So these are equal. We're going to ignore the 0. You can't divide by 0. Here I've got negative 1 to 1, which is still equal to negative 1. And then finally, I see negative 2 to 2, which again is equal to negative 1. So I see that all of these ratios are equal. This is telling me that I actually have ordered pairs that are proportional, which means I have a proportional relationship. What does that mean? It means that if I look at the graph, I should get a straight line that passes through the origin. Well, let's just plot these points and see if, in fact, we confirm that hunch. So negative 2 for x gives me a corresponding y value of 2. So that means I go negative 2, so left 2, and then up 2. So that's negative 2, 2. Then I have negative 1, 1. So negative 1, up 1. Then I have 0, 0. That's good. It's got to pass through the origin. It's looking good. I've got a 1, negative 1. And I see 2, negative 2, 2, negative 2. Notice all those points do lie on a line, and that line passes through the origin. So in fact, our intuition and our hunch was absolutely perfect. In fact, this function is, in fact, giving us a proportional relationship. Absolutely cool. Absolutely cool. Straight line through the origin. Isn't that cool? Great. Let's try one last one together, just for fun. Relax. We'll have some fun. Here's the function. Y equals x minus 3. This is looking good, looking good. Let's make a little chart, a little table of some points, see what's going on. So I'll pick 0, 1, 2, 3, 4 for my x values, and now we'll find the corresponding y values. What's the function here? You give me x, I take that value and subtract 3, and that yields the y value. So when I insert a 0 for x, I see 0 minus 3, which is negative 3. So I see negative 3 for y. When I let x be 1, I see 1 minus 3, which gives me negative 2. If I put a 2 in, 2 minus 3 is negative 1. 3 minus 3 is 0. And 4 minus 3 is 1. Okay, let's take a look at ratios, non-zero ratios, x to y to x. And let's see what we got. So non-zero, so I'm going to ignore the zero things here. Let's take a look at this. So here I see negative 2 over 1, perfectly fine ratio. The next ratio here is going to be negative 1 over 2. Now notice that negative 1 over 2, which equals negative a half, is not equal to negative 2. So already, we're done. We're done. We are in big trouble. This is not going to be a proportional relationship. Let's just keep trying. Can't do the zero part here. Let's look at this here and see. You could do the zero. 0 divided by 3 is 0, but let's forget that. And let's look here at 1 to 4. And 1/4 is not equal to negative 2, and it's not equal to negative a half. And so we see this, in fact, is not giving us a proportional relationship. So one of two things must fail. Either it's not a straight line, either it doesn't pass through the origin, or both. It's neither a straight line nor pass through the origin. Let's see why this fails by graphing this function and seeing what happens. So we've got the points. Let's just plot away. Let's see. We've got x equals 0, y equals negative 3. So 0, negative 3 is right here. Then I've got 1, negative 2. So 1 over, and I go down 2. I see 2, negative 1. So 2, negative 1. I see 3, 0. So that's on the x-axis. And then 4, 1, 4, 1. They all look like they're on a straight line to me, so we definitely got the straight line thing going. So what must happen? It must be the case that it doesn't pass through the origin. And if you look at the picture of this straight line, you'll notice that, in fact, it doesn't pass through the origin because it crosses the y-axis not at 0, but at negative 3. So, in fact, once I got to this point right here, I saw that when x equals 0, y equals negative 3, I knew I was done. Because, in fact, to be a proportional relationship, you've got to pass through the origin. And we see here that this function has a graph that's a straight line, nice, but doesn't pass through the origin. Not so nice, if you're valuing your niceness on whether you're a proportional relationship or not. Proportional relationships are great. They're describable graphically as straight lines passing through the origin. And I'll see you soon.
All right, a quick review via the lesson tutorial. Identifying proportional relationships. Tell whether the function is a proportional relationship, then graph the function. So first, they give us the function y is equal to x minus 3. We make a table. We make our own x values, 0, 1, 2, 3, 4. We plug the x values in to find our y values, and we came out with negative 3, negative 2, negative 1, 0, 1. Then we try to find our slope, our direct variation, or our constant rate of change. All that means the same thing. It's a fancy way of saying rise over the run. So y over x, and we look at all non-zero situations, like we don't put this in, we don't put that in. All right. And we end up here with a negative 2 over 1. That does not equal a negative 1 over 2. That's that one. Doesn't equal that one. And it doesn't equal 1 over 4. So none of these are equal to each other. The ratios are not equal. So the ordered pairs are non-proportional. Next, we graph the ordered pairs. All right, next we graph the ordered pairs from the table. So after graphing, this is what we got. All right, the graph does not pass through 0, 0. So the graph is not going through there because it has a y-intercept. And the y-intercept in this case is 3. The ordered pairs are not proportional, and the graph does not pass through 0, 0. So y is equal to x minus 3 is not a proportional relationship, even though it's linear.